Hello, hi everyone. I welcome you back in this room. This is time for Luca Bruno that will talk us about oxidizing RPM-ostree.
Okay, check.
Thank you.
Perfect, thank you. Welcome. Okay, so first of all, thanks for being here, despite the food coma, because the food was great and in good quantity. So my name is Luca Bruno, as has been introduced. I'm going to talk about oxidizing RPM-ostree. Oxidizing is one of the topics of this RustLab conference. So you already more or less know what it means, like porting something to Rust, something that maybe initially was not completely in Rust. And RPM-ostree is a project that I'm working on. It's a free software project, and most of you, I guess, have never heard of it or don't know it at all. I'm going to give you like a lengthy introduction, and then we're going to dive into the oxidation part. For those following remotely or even here, like my slides are online on speaker deck. And on several pages, you will find those small icons. They are like hyperlinks to the projects, to several libraries that we use, and to other interesting pages that I'm going to mention. So let's start. First, who am I? I'm a computer engineer. I'm Italian, yes. I work a bit here, a bit there, like I move across Europe. Right now, I'm based in Berlin, but I'm currently relocating. I've been doing like free software, open source for like many years. Currently, that's my main job as well, and I love it. I am part of CoreOS, which was like a small startup, and we later got acquired by Red Hat, which I guess like most of you already know. It's quite a big Linux vendor, and there I work as a software engineer, like a senior software engineer. And my focus, which is among others, is one of the projects that I'm talking here. It's in general on the user land side of Linux. That means like not the usual kernel development, nothing like high-level backends or containerized application or things like that, but mostly like operating system components themselves. I didn't mention it here, but like my company and also like my organization is mostly all in into Kubernetes technologies, and in general we do a lot of like modern development in that area. But my focus is mostly on the low level of the stacks. That means the operating system itself. And before joining CoreOS and Red Hat, I was working as a security researcher. So let's start. That's the overview more or less of this talk. The first part, which is also like the largest probably, it's a lot of introduction to components, because like I don't expect most of you to be familiar with those projects. And we are going to introduce a lot of libraries, Rust libraries, that are super useful to what we are building. So we are gradually building this journey through the projects. So please follow with me, and I hope I'm not going to lose yourself. So let's focus right now on the introduction. An operating system is made of a lot of components, a lot of technologies. Some of those are older and some of those are newer. In our case, we are only going to focus on a specific operating system that is like a Linux-based operating system, and we are going to focus on these new components that are like made in Rust, and some of those old technology that we keep using because we are not going to rewrite the world right now, right here. The scope of the problem, the scope of the project that I'm working on is the following. We do build a Linux distribution. We do build several distributions. Red Hat is selling several products, several distributions. The one that I'm caring about, the one that I'm focusing on, are the so-called hermetic distribution, which means in a way different to the usual distribution that you may have seen, like Debian and Ubuntu. An hermetic distribution is mostly self-contained, and it comes as an image. You might think about like the Amazon AMI, that you don't get an installation disk before booting the machine, but you directly get the image. Kinda like that. In our case, in particular, we are focusing on a specific kind of hermetic distribution, which are those based on RPMs, because again, like my employer, it's all into RPMs. And after that, we also focus on like distributing them as OS3 commits. I'm gonna talk about both of those technology later on. So the chain, like the pipeline, flows more or less like that. We start with a lot of source tarbles, like the Linux kernel, systemd, the GNU libc, and all the other libraries and applications that you usually have on a Linux machine. Those get compiled into RPM packages. We're not going to focus on this step. We take it as granted, more or less. But those packages still need to be more or less like unpacked, like exploded, put together, and then transform into these OS3 commits that I'm going to describe. And this is the actual step where we are focusing. And then, of course, there is another step after that, which is you need to get some image at some point to install or directly to boot, which means an AWS image or some kind of like Metal image or an Azure image or whatever it is that you can actually use. So the first component is RPM. Many of you, I guess, already have seen it or already use it. It's a fairly old software format, like format for software packages. Like this is from the 1995, which is more or less like as old as the Linux kernel itself. It's slightly newer. It's more or less the age of many of you in this room. So you may guess that like we do use legacy technology in the sense that we don't invent everything like from scratch. We don't start writing things from scratch. We do reuse a lot of stuff. And RPMs are useful for carrying this binary data, so the executable themselves and other data. They do declare dependency between them. And one thing that I like to focus here and stress here is that RPMs can also run pre-installation and post-installation scripts. And of course, like this format is still in use, like Red Hat is still using it for its own RHEL product, and other distributions like Fedora and OpenSUSE are using it as well. Then the second component in our project is this OS3. OS3, like while I do expect most of you to already have seen an RPM, OS3 it's kind of like a not so well-known technology. I usually describe it as a Git-like manager for your bootable file system, the file system of your machine itself, the operating system. It is Git-lite in the sense that it supports multiple repositories. It supports like pulling from those repositories, pushing from those repositories, and in general, it keeps some kind of like version history with branching and merging. One interesting thing, the things that we do care here is that we do use this technology at the operating system itself, which means that we focus on how to perform upgrades and how to switch between versions of the operating system. Many of you may have like an Android device, a Chromebook, a Chrome device, or whatever. And if you have looked into the technical details of that, you know that when you do an update, you do download the new version and you store it into your device, and then you reboot into the new version. But the old version is still available. There is another partition, and the bootloader switches between the two. This is what in the slide is called the the multiple AB partition, which means that at any point there is an active partition for the operating system and a passive or secondary partition for the operating system, and the bootloader knows which one to boot. And that's how you get like upgrades and rollbacks in a transactional atomic way, let's say. The difference here is that OS3 doesn't require you to have this double partition, double space. We do use like a single operating system partition. And then there is this OS3 manager, which is kind of performing the same job as Git, in the sense that in the same Git repository, on the same file system, you do have multiple versions of your software, of your projects. And here we do the same for the operating system. You see, on the left, we start with our operating system at version 1, and then we say, okay, now I want to pull version 2. this version 2 gets downloaded, you see the package, it gets stored into the same partition, and now suddenly you have two versions of your operating system, version 1 and version 2. There is a bit of, let's say, magic here, which is actually like storage, like space optimization, so that we don't duplicate the whole data. But when you're in that situation, then you can say, okay, now I want to reboot, and I want to boot into this new version. And if something goes wrong, you can also say, okay, but if it failed, if the boot failed, then I want to go back into version 1. And this is the point of OS3. And this is kind of like a not well-known project, but it's in the embedded world, it's kind of used and kind of useful for those that are approaching this firmware update in a way which doesn't require the double partition scheme. So like in the Linux world, that's one way of doing upgrades. And in other devices, like network switches or things like that, you usually get like the two partition. So putting everything together, this is the focus of our talk, actually. It is called RPM-ostree. Yes, we don't have any fantasy. We are not very creative people. We are engineers. So as you can imagine, RPM-ostree is a project that takes RPMs and OS3 and puts them together. That's all of it. So the idea is, again, like bridging between those RPMs that we already have, because distribution are already building them, and OS3 that we use for this kind of like transactional update scheme in order to build an hermetic operating system. As an input, we take a set of binary packages. In my case, that's my job. We take the RPMs from RHEL, in the case of the product, or from Fedora, in the case of our project. And that's the set of, that's the input set. And on the output side, what we produce is an OS3 commit. This OS3 commit is what the machine, the Linux machine that are running our operating system are actually downloading for the network, storing locally, unpacking locally, and using as their own booting operating system. RPM-ostree itself is made of several components. It's a fairly large and complex project. One side, it's a client daemon part, like it has this client daemon architecture. It is what you actually get running on your own machine, and that's where you can use the CLI, you can use the command line in order to say, okay, I want to pull this version, I want to reboot into this version, or I want to roll back into the previous version. And then there is another part which instead doesn't have this client daemon split. It's a monolithic CLI application. And that one is what we run for building the operating system itself. You remember this input to output translation. And usually we do build the operating system inside of some kind of like container orchestration, some cluster where we can schedule our containers. And so this is like a single CLI that runs inside a container, and it does this transformation from RPMs to OS3. Okay, I think I haven't forgotten everything. So that's where we are. This is the introduction to the components that we're going to touch. And our goals as RPM developers was more or less the following a few years ago when we started this oxidation process. More or less stopping writing new code in C. Not because we are not C developers or because we completely dislike C or whatever, but for several reasons that I'm gonna list later in the conclusion, which makes our life easier. That more or less means, well, there are two options for doing this. Like, either we stop completely developing this software, which is like, yeah, if the software is done, there are no bugs, then cool. And that's not the case, unfortunately, for us. And that's also why they pay us. So it's better to keep writing the code. And the other alternative for us was looking into some safer and better alternatives, and which means like trying to write the new logic directly in Rust. A side effect of this kind of like stopping on one side and starting in another direction means that gradually, over time, we are reducing the amount of C and C++ lines that we have inside the project. I'm mentioning C and C++ here because like this project has more or less like all the legacy Linux stuff that you may have seen. Like it's a bit of a mess inside. So we do have some C component, some C portion of this code base. We do have some C++ component inside this code base. So overall, it's not like this one of those new clean code bases where you can say, okay, it's only Rust with a small bit of C or vice versa, whatever. It has everything. It's a real life case. And again, like I don't want to I don't want to rewrite everything. Like we didn't want to rewrite everything in Rust right now. I'm going to give you some numbers later. What we wanted is more or less like a gradual transition where we keep what we already have working, and on the side we start pushing in a new direction, a different direction, which is more or less the whole idea as well behind RPM-ostree. Like we are not inventing a new Linux distribution from scratch. We are not inventing a new world from scratch. We are bridging from what we already have, which means in our case it means RPMs, and we are transitioning into this other world where we handle OS3 commits. But there is this bridge. We are building new technology on the OS3 side while still keeping one foot inside the old world of RPMs. Okay. So we're going to start looking into the actual journey. This is our map. There are a few components that I would like to highlight. As you can see, like they are, some of them are more famous. Some of them, I don't expect any of you to ever heard of it. Some of those, it's something that we wrote ourselves, and some of those, like, no way that we could have written it just from the time that we have, like from our resources, because this is how the free software world works. It's a mixture of several efforts. So we're going to touch into several components. I'm going to start with this one, glib-rs. So introduction here, I'm sorry, there are going to be like a lot of introduction for legacy technology before looking into the new world. Glib, it's a library, it's a C library. For those that may think of it like, I know this is the GNU libc. Okay, that's not it. It has a very confusing name. It's completely a different thing. It's unrelated to GNU. It is part of the GNOME landscape, and it is one of those like C libraries that if you are writing your own C software from scratch, then you're going to implement an hash map, a linked list, some kind of like configuration format, bunch of other like threading helpers and things like that. Okay, that's exactly what it is. Like glib is this library. It's basically some share code that all the GNOME application back in the days they used to have. So at some point the GNOME developers they put it all together in a single place. That's the glib library. We do use it because again, like when this project started many years ago, it was a C project, and we didn't want to invent our own hash maps and lists and everything else. And so we were kind of like close to the GNOME world anyway. And so that's what we use on the C side. That's great because it means like we already have a lot of primitives on the C side, both OS3 and RPM-ostree. They are using it in many places, which is great. Again, we don't have to reinvent the wheel. The problem now is, okay, we do have all these structures, and somehow we do have the same structure on the Rust side. We do have hash map, we do have lists, we do have like trees, configuration, and everything else. And so I would like to say thank here to the GNOME people, because since several here they are doing a huge push into the Rust direction, and so they have like this large organization called GTK-RS, and inside this organization, under this umbrella, they are maintaining all these kind of like bridges and gluing, which let us mix without too many troubles the glib side, which means like the C structure, and the Rust structure. Like if you look at the code on the right, this is a mixture between the usual like string and buffer readers and usual things on the Rust side. Like this is not particularly good code. I just copy pasted it from somewhere. And then at the bottom, we are switching to the glib side for parsing configuration file. Like this key file format is the same that is used by many, many applications in the GNOME land for parsing their own configuration. Then another one, still staying on the GNOME world. One problem that you have if at some point you wrote a C library is that you want to bind it from several languages like Python, Ruby, whatever, and Rust as well. You can do it manually. You can use cBindgen. You can use a lot of technology. These are kind of like newer technology, let's say. GNOME is kind of like a old project. So what they invented is this kind of annotation, this kind of like intermediate representation, which is called GIR or GIR, to describe the public API. You can see that it resembles more or less some Rust ideas. Like this is a pure like C annotation, and you can say, okay, you know what, this pointer allow none. It's basically like it's an option. It means that you can pass a pointer with an actual value or a pointer with a null value to signal that this is a none, like there is nothing here. And then you can see that on the return side, there is a transfer, which means like, hey, the result here is not a borrow, it's the full ownership that is getting transferred to the caller. And there is like an automatic translation tool called GIR that takes this kind of annotation and translates it into whatever is the language that you're targeting. And in our side, in our case, we are targeting Rust. And so we do have this library like lib-ostree, which is annotated with this GIR annotation. And we do automatically generate two crates out of it. One, which is the lower level, which contains a lot of unsafe. You can see it on the code on the top box. All of that code is automatically generated from the annotation. We don't do anything to it. You see it's quite nasty. There is unsafe. There is a lot of like pointer juggling. Yeah, maybe not because, in this case it's not very apparent, but there is like some pointer juggling going on. And you don't want to touch it pretty much. Like you don't want to deal with this. What you want to deal with is the bottom side, which is what you would use as a Rust consumer, which is the OS3 crate. And on that one, you see it's the usual Rust code that you're used to. Like you can pass like enums as flags and proper things, and you get like error handling, the question mark, try, and everything else. And there is no unsafe in here. So this is a usual split that you often see when binding to C library. In our case, the only difference is that the C side, like the low-level C crate, it's automatically generated from the annotation. We do go one step farther from here, which means instead of just implementing everything in C in the lib-ostree library, from time to time we do want to sketch something quick or implement new feature that we are not sure about. We don't know like how the consumer is going to look like, if there's going to be any consumer, if we went in the wrong direction or whatever. Let's call them like experiment or optional features. And what we started doing was adding another crate. So this extension crate, as we call it, OS3-X. And in this crate, again, we don't write any kind of unsafe, any kind of like weird C-like code. We just write pure Rust. And even better, in this case, we are completely detached from the C world, from the GNOME world. And we can say, okay, here we are really starting to unlock the power of the Rust ecosystem, which means we can use serialization and deserialization through CERD, without having to link to some system library or things like that. We can use like asynchronous code using Tokyo or any other like async runtime, and so on and so forth. And that's great. Like this improves our developer lives a lot. Then the other component that I'm talking about, it's a step in a different direction. So far we were focusing on the OS3 side, which is mostly like coming from the GNOME world. It uses a lot of GNOME technology. Then we have another side as well, which is the RPM side. On that front, I'm not gonna go too much into details because it's a bit of like dirty and still changing as a landscape. But we do use libdnf for handling RPMs, which is a bit of like an higher level library for handling RPMs. It has a very large surface because it knows how to handle like installing and uninstalling RPMs. But at the same time, it also handles like repositories, signatures, and things like that. And inside RPM-ostree, we don't use all that power. We don't use all that features. So what we did instead of like creating another binding crates and things like that, we are just like using some internal code, some internal bindings, only for the few things that we care about. And these bindings are kind of like interesting. If you look at this, in this snippet, there is no unsafe block. There is nothing. There is not even like the body definition. There is pretty much nothing. And this is all the binding. That's actually the code that we have inside. If you squint your eyes a bit, you see that there is something a bit like strange or sketchy. There is one strange type, which is called FFI DNF package, while the type that we are looking at here is this DNF package, which is some kind of like Rust type. The catch here is that we use another project called CXX RS, which is great, honestly. This is great. It's one way of bridging between Rust and C++. As I mentioned before, like we already in this situation where we have a mix of like C, C++, and whatever. And so at some point we just said, okay, let's look into some way that makes our life easier, instead of like writing every single binding, every single glue code, doing all this kind of like tricky FFI and pointer dance. And more or less at that time, we found, and it came into existence, this CXX crate, which is, it has a lot of magic, honestly, inside. But it is a way similar to CBindgen for generating this glue code between C and Rust, actually between C++ and Rust. And in our case, the great thing is that it is pretty much hiding all the bridging between the two. As you can see in the diagram, you do get a proc macro, this CXX bridge. You do put in there the description of what you want to bridge. And then you get two sides. You get Rust binding on one side and C++ binding on the other side, which is kind of interesting because in this way, you actually have bidirectional access to the code that you are writing. So if you're writing new Rust code, you can access it from the old C++ side. But if you already have an existing C or C++ library, then you can access it from the Rust side. And you don't have to write the glue yourself. You don't have to deal with FFI. You get something similar to the previous slides where you just say, okay, these are the signatures, these are the functions, these are the types, and then CXX takes care of matching those between Rust and C++, depending on which direction you are going in this bridge. And the bridge itself is mostly hidden. You don't see it. Okay, so those were kind of like super interesting component that makes ourselves easier. If I have time, I also have some backup slides for later with some more interesting components, but let's now dig into the oxidation process itself. So let's dig into RPM-ostree itself. Again, like I want to put this in perspective. Many of you are dealing with software that are kind of like new. Let's say they have been written in the last 5 years, 7 years, something like that. The first release of RPM-ostree was in 2014. And itself, it's using technologies like RPM and OS3 that are even older than that. So when this started, more or less, Rust was kind of like just a glimpse into the future. And so this was just another like typical C Linux project. Currently, as of today, we do have the new release, like 2022.13, which contains way more commits. Like you see, like we went from something 30-something to 5,000 and more. And in the meanwhile, we had like more than 100 releases. So many things changed in the meanwhile. If we go through history, the project started in 2013. And when it started, for a very brief amount of time, it was actually a Python project. It was one of those like small project that you start for gluing some C library, C code that you have into something which is a bit easier to hack around and to use. But then soon, like a few months later in 2014, it became apparent that this project was kind of low level. It needed access to many low level features, for example, like SE Linux manipulation or file deduplication through hard links, or like dealing with multiple root file system mount points and things like that. And so it was ported to C. And again, like this is where all those GNOME, glib, and other things came into play. Then fast forward many years. In the middle here, there was like the acquisition. Many things changed. And in 2018, we started toying with an idea, which was like adding some logic in Rust to this project. Sorry, my timer went off. As an opt-in feature, which means like we were not sure. We were kind of like, okay, this looks nice, but let's try and see how it works. And then the experiment was quite successful. 1 year later, we moved more logic, especially like core logic on the Rust side, and that became no more an opt-in, but something that was compiled by default. But at the same time, like we had to bridge a lot of things from the C side, so there was a lot of manual FFI glue. And then fast forward another year. At that point, we saw this other project, this CXX project, and we say, okay, you know what? Let's try to push a bit more into the C++ direction, because anyway, we already have some bits in C++. And let's see if we can actually use the full power of this CXX bridging. So that was like the timeline in years. And instead, this is the timeline from a point of view of the code base. In 2018, as I told you, like there was one first release where we started adding some Rust code optionally. It was more or less like 300 lines of codes. It gets basically lost in this pie chart, but if you can see the number, it's 0.8%. But it was a start. Like we started experimenting a bit. And in 2020, so 1 year and a half later, the percentage was already almost 10%, let's say. But the process, as you see, like 1 year and a half for 10% of the code base was very slow. This is where, again, like in 2020, this is where we decided to try this C++ CXX thing. And so we moved into this direction. Now, if you look at the numbers, the Rust side here is more or less the same. It moved from 10% to 11%. But there is a large chunk, like 1/4 more or less, of C++ code that we had to introduce at that point for bridging, for using those things on the C side and on the Rust side. And then we went completely all into that direction. This is the state nowadays. You see like latest release in 2022, where we do have a very small portion of C for reason that I'm not going to explain. But most of the project now has been converted to C++. It's a bit of a weird C++. It's mostly C compiled by C++ compiler. But it is technically C++. And the Rust side, as you can see, like it has seen a quite big growth. Like we moved to like 1/3 of the whole code base, because using this automatic bridging, it is way more easier for us to write code in Rust and then directly use it on the C++ side without having to manually add all the glue. And so we learned a few lessons while doing here. I'm gonna split them more or less in two categories. Like one category is related to the development flow itself. And the other category is related to the ecosystem and how to ship the software. So indeed, on the development flow, which is the one where I'm mostly exposed to, it was great. We did increase the usage of unit tests, like writing unit tests in C was a bit of a pain. RPM-ostree has a huge integration test suite, but that takes a long time to actually run. You need to build an image, boot a virtual machine, then try these kind of like upgrades, downgrades, and things like that, and that takes long. Unit tests are way quicker. They test something completely different, but they are very useful. Then code formatting with Rust format was kind of like a breeze. So we started like from day zero, we started with that. While the C side was, one of those like, a bit of anarchic and chaotic situation. But given that we were using Rust format, formatting the Rust side and enforcing that on CI, then we spent some time doing the same things on the C side as well. And now as a result, we do have both the Rust side and C++ side, which is formatted automatically and checked in CI. And from my side, from a human side, like when you do get a pull request and you need to review it, I do appreciate the new situation, the new world. Like as a reviewer, I'm able to focus on the logic on the code, on the design of the code, instead of like checking, are you missing a null check here? What is the ownership of this pointer that you're pointing? What is the validity, the lifetime of these C pointers? Because the same ideas that you have in Rust, like the lifetimes and the ownership and so far, you still have them in the C world. Like when you have a pointer and it's pointer to some and it's pointing to some kind of object, you still need to take care of like the ownership and the lifetime. It's just that you don't have any help from the compiler. You need to write it, you need to check it, you need to take it into account in your mind. And that kind of like it's bothersome. And then on the second side, the how to ship the project. In our case, again, like you may be used to shipping project in containers. You may be used to kind of like automatic CIs and CD pipelines and things like that. In our case, we are shipping an operating system, which means like you need to build all this stuff. You need to put it into the base image. And if you screw something, then even recovering from this state, it's very hard. Like you are writing the software that takes care of operating system upgrades, and if you screw it up, then you cannot upgrade and you cannot roll back, and you're kind of like, not great. And on top of that, you need to be versioned with the rest of the operating system, so you need to use whatever compiler is in the distribution, whatever libraries are in the distribution, and so on and so forth. So we had to figure out a bunch of things in order to ship this code into Fedora and in RHEL, which are kind of like similar, but they do behave in different way from that point of view. And we did have to pay attention to the minimal toolchain version. So in this case, it was kind of like, as a human, we need to take care, but let's put this check into CI so that we can automatically have a yes or no verdict. And on the positive side, doing this, we gained access to a lot of library. I mentioned like all of them before, and CERD and Tokyo and other things from the Crates ecosystem. And at the same time, we were not anymore too much dependent on whatever was on the operating system. Like, we don't need anymore a JSON deserialization library being in the operating system. We can use it from the Rust side itself. Okay, that was pretty much it. I do have a bunch of backup slides if you want, but I can also take questions if you prefer. So my backup slides are on a very low level, which is like mostly interfacing with the POSIX interface, the Linux, Unix low-level interface, which is what we do on a very large portion of this code base. We do use some crates. You may already know this Nix, which is a wrapper around the libc primitives, which tries to be safe and helps you trying to avoid like those food guns that you usually have with the C APIs. And again, like it was great. We used it for a long time. There was one minor thing that was kind of like beating us quite often, which was related to the file descriptor. Like if you look at this simple call, like this is just sim linking things in place. We do use some path, like some relative paths, some target for the symlink, and then there is a directory file descriptor. In Rust, for a long time, those file descriptors used to be plain integers, which means you would open a file, get a file descriptor, which was, I don't know, let's say 10. And then somebody else in some other place would get this file descriptor, which was an integer, and copy it, because an integer has a copy trait automatically implemented on it. And so suddenly you would get like two objects, two structure, two entities pointing to the same file descriptor or the same open file descriptor, but then with a decoupled lifetime. Like on one side, you may want to close it, while the other side doesn't know about that. A major change up recently in the Rust standard library. So as of the 1.63 release, we did get this IoT safety feature, and that's very recent. Like this was in August, and this one introduced like safe primitives for file descriptors, similar to the borrowing that you can get versus the ownership. Now you can do the same with file descriptor, and on top of that, so 2 more crates appeared from the same person that were pushing for this IoT safety rework. One is Rustix, which is similar to the crate that I showed you before, Nix, for accessing the POSIX API, but in a way which is IO safe. It means like that it knows when a file descriptor is borrowed, when a file descriptor is owned, and what is the lifetime of it. And then on the side of it, another library called CAP standard, which stands for capability standard. It's a reimplementation. It's a version, let's say, of this the standard library primitives based on capabilities. Capabilities are a security concept that is useful for building sandboxing, in this case, like file system sandboxing. And in a very, very short way to put it, it's something that helps you avoid security bugs. For example, the infamous let me leak /etc/password by saying, okay, .. // password, which means just like go parent from parent to parent to parent until you get to the top directory, and then you open passvd. Okay, that's the way to avoid it, via getting a proper capability that says in which subdirectory you are confined, and then your sandbox is there. Okay, sorry, I went a bit quick through the backups. I don't know if we have time for question.
So thank you, Luca, for your talk. If there are any questions, okay, one.
And I'm going to take more questions outside, because otherwise we take more time.
Thank you for your presentation. Maybe this question has already been done multiple times, but how do you go over the limitation of the platforms Rust compiles to, having a kind of distribution? You don't ship for those platforms?
We do. So I do work for a company that is selling Linux product on PowerPC, on S390X. I didn't mention it in the slides, but we have been acquired by IBM. Like, it's no news that Red Hat is part of IBM. So we do support all the IBM platform. And so we do target pretty much like all the 64 architecture that exists, which means like AMD, ARM64, PowerPC, and S390X. And yes, we do take care of that. Like there are actually a lot of people that are working on making sure that Rust and Rust-based application work on those platforms, and then internally we do deliver those projects on those platforms, both in Fedora and in RHEL. Please.
Hi. Did you also try out transpilers from C to Rust?
Something like the C to Rust, things like that?
Yeah, I don't know what is the current one. There were like several over the years. I think no one made it.
Okay, so personally, yes, on some like small, mostly self-contained project. In this case, RPM-ostree was kind of like one of those like large project with a lot of like dependency on things. For example, like we do dbus, which means we use like glib dbus library with their own event loop and everything else. And so transpiling our code would have been kind of like interesting, but then we were still missing all the bridging between like all the other libraries that we use, like OS3, DNF, all the other GNOME things that we have. So it's like, we didn't try on that project because we didn't feel that it was kind of like an interesting experiment for the future. Like the problem is not with the existing code base, like the C side, yes, is still there. We do kind of like port, for example, like parser, we do manually port them, adding unit tests and things like that, but not automatic translation.
So maybe a little bit a side question, but should be still relevant, about CXX RS. Say I didn't know about it, so I would ask something like an evaluation about how production ready you consider it, if it's how to say full of pitfalls, or it helps you to avoid pitfalls, or these kind of things.
So I would say, like, from my side, it's working great. Like, compared to the manual bridging that we were doing, like, as a human, we do way more mistakes than the translation that CXX can do. It has a lot of limitation, like it cannot translate some kind of like complex types or whatever. For example, like I don't remember if the option type, the option modded can be directly bridged, or you need to do some kind of like manual workarounds in that case. It got mentioned in a previous talk as well, like there are some limitation on the way that you write things. But from my side, it's kind of like it's better from a development point of view, and from a runtime point of view, it doesn't really appear in the final things. It's kind of like it's a compile time bridging, and so you get like the library itself. It has been written already and validated by many other projects as well, and that's fairly stable. And then you have like your own bridging, your own kind of like assembling the things, where of course you can make mistake, but it doesn't involve like unsafe and pointers switching and things like that. So it's like there is a less way of making huge mistake, let's say. So that's my feeling, at least.
Thank you. Any other question on the other side?
Hi there, thanks for the talk. If you could do it all again, would you just go at it and rewrite it in Rust from the start if you knew everything that you know now, or would you still take the path that you've taken now with everything you've learned? Obviously, it's hard to say, but...
So a time machine back to 2013, 14. It also depends on the Rust ecosystem itself. For example, like there are many things that the C and GNOME ecosystem in this case already went through and tried to solve in some way. Like the ownership thing, you can see it's similar to Rust, and like Rust on that side is kind of like better. Like the compiler already know about that, and you can directly statically enforce it. But then there are a lot of other things on the ecosystem side that exist in the GNOME world. For example, like canceling things was already something that they had, like thread pools and kind of like RPC, like dbus or things like that. That was already kind of like a solved thing, like something that had a solution already years ago. So I would say that like the optimum would be getting a few years farther from here, where we have even more libraries, like even more asynchronous things settled, let's say, stabilized and completely done. And then at that point, getting a time machine and getting back. Okay.
Thank you.
Thank you.
Any other? Okay.